A cylinder is one of the most basic curvilinear geometric shapes, the surface formed by the points at a fixed distance from a given straight line. The axis of the cylinder, the solid enclosed by this surface and by two planes perpendicular to the axis, is also called a cylinder. The surface area and the volume of a cylinder have been known since deep antiquity. Common use. In common use, a cylinder is taken to mean a finite section of a right circular cylinder, i.e., the cylinder with the generating lines perpendicular to the bases, with its ends closed to form two circular surfaces, as in the figure. If the ends are not closed, one obtains an open cylinder, whose surface is topologically equivalent to an open annulus. Volume. If the cylinder has a radius r and length h, then its volume is given by V equals pi r2h. Having a right circular cylinder with a height h units and a base of radius r units with the coordinate axes chosen so that the origin is at the center of one base and the height is measured along the positive x-axis. A plane section at a distance of x units from the origin has an area of a square units, where or an element of volume is a right cylinder of base area awi square units and a thickness of delta x units. Thus, if v cubic units is the volume of the right circular cylinder, by Riemann sums using cylindrical coordinates, the volume can be calculated by integration over surface area still using a radius r and length h. The surface area of a cylinder is made up of three parts: the area of the top, pi r2, the area of the bottom, pi r2, the area of the side, 2 pi rh. The area of the top and bottom is always the same, and is also called the base area. The area of the side is also known as the lateral area. An open cylinder does not include either top or bottom elements, and therefore has surface area L equals 2 pi rh. The surface area of a closed cylinder is made up the sum of all three components: top, bottom and side. Its surface area is A equals 2 pi r2 plus 2 pi rh equals 2 pi r equals pi d equals L plus 2b, where d is the diameter. For a given volume, the closed cylinder with the smallest surface area has h equals 2r. Equivalently, for a given surface area, the closed cylinder with the largest volume has h equals 2r, i.e., the cylinder fits snugly in a cube. Cylindric sections. Cylindric sections are the intersections of cylinders with planes. For a right circular cylinder, there are four possibilities. A plane tangent to the cylinder meets the cylinder in a single straight line segment, moved while parallel to itself. The plane either does not intersect the cylinder or intersects it in two parallel line segments. All other planes intersect the cylinder in an ellipse or, when they are perpendicular to the axis of the cylinder, in a circle. Eccentricity of the cylindric section and semi-major axis of the cylindric section depend on the radius of the cylinder r and the angle between the secant plane and cylinder axis alpha in the following way. Other types of cylinders. In differential geometry, a cylinder is defined more broadly as any ruled surface spanned by a one-parameter family of parallel lines. A cylinder whose cross-section is an ellipse, parabola, or hyperbola is called an elliptic cylinder, parabolic cylinder, or hyperbolic cylinder respectively. An elliptic cylinder is a quadric surface, with the following equation in Cartesian coordinates. This equation is for an elliptic cylinder, a generalization of the ordinary, circular cylinder. Elliptic cylinders are also known as cylindroids, but that name is ambiguous, as it can also refer to the pluccoconoid. The volume of an elliptic cylinder with height h is even more general than the elliptic cylinder is the generalized cylinder. The cross-section can be any curve. The cylinder is a degenerate quadric because at least one of the coordinates does not appear in the equation. An oblique cylinder has the top and bottom surfaces displaced from one another. There are other more unusual types of cylinders. These are the imaginary elliptic cylinders, the hyperbolic cylinder, and the parabolic cylinder, about an arbitrary axis. Consider an infinite cylinder whose axis lies along the vector. We make use of spherical coordinates. These variables can be used to define A and B, the orthogonal vectors that form the basis for the cylinder. With these defined, we may use the familiar formula for a cylinder, where r is the radius of the cylinder. These results are usually derived using rotation matrices. Projective geometry. In projective geometry, a cylinder is simply a cone whose apex is at infinity. This is useful in the definition of degenerate conics, which require considering the cylindrical conics. Related polyhedra. A cylinder can be seen as a polyhedral limit in case of an n-gonal prism where n approaches infinity. It can also be seen as a dual of a bicone as an infinite-sided bipyramid.